Okay, we're recording now. Good. All right. The thing I have up here is the formula sheet that comes with the quiz that will be handed out with quiz number 2. This is posted on the D2L webpage, together with the practice quiz for quiz number 2. That's already up there. And the thing I want to mention here is that there are a lot of good stuff on this formula sheet. However, there's a few things that are not on the formula sheet that you should bear in mind in case you will have trouble without the formulas. Okay, so I'll let you know beforehand. And these things here, okay, 9.81, because that's actually the values that are going to be used in the multiple choice responses for the quiz. So it will actually be 9.81 rather than 9.80, but don't let that bother you. Okay, some conversions here. You've seen this before, quadratic equation, vectors, derivatives, integrals. Then you have the average, A average, instantaneous, VA, and then the kinematic equations for VA. Okay, and then there's this formula for the relative velocity. Now you have to get used to what that actually means. The way I like to say it is, if you have the velocity of A is equal to the velocity of B plus the extra velocity of A relative to B. That's how I like to write it. Okay? Or the way it's written here is C relative to B, C relative to A relative to B. That's what the meaning of these things are. Okay. The other thing is we have this for the arc length delta S is R times delta theta, where theta is in radians. Okay, and then you have this for the speed. The linear speed is v is equal to r times theta, omega. But then you have the tangential acceleration is r times alpha. Remember, alpha is the angular acceleration. And then you have the centrifugal acceleration, or the radial component of the acceleration. It's v squared over r. That can also be written as v times omega. Okay, and this is omega being the angular velocity. And omega squared times r is also another formula for that guy. Now, and then there's Newton's second law, A is equal to F net over m, and Fg, the force due to gravity on the surface of the Earth, is mg straight down. Now, the things that are not on the formula sheet that you're supposed to just know, all right? I'm telling you this so that make sure if you don't know it, you do know it. Okay. So the circumference of the circle is 2 pi r. When you talk about things going around circles, you have to know how far that distance is, right? There's another formula for the tangential acceleration at, the component in the tangential direction. It's the derivative of the speed with respect to time. You can pull that out from combining some of these formulas here, but maybe that's a little non-trivial. So just remember that, or get used to using that. And then there's just the definition of the angular velocity omega. Omega is d theta by dt, the time derivative of the angle. And then the instantaneous angular velocity. And then the angular acceleration is the derivative of the angular velocity with respect to t. Okay, is everybody good on that? The reason these are not put on this formula sheet is, is my understanding is because they're the same sorts of things. They're the analogs of these things. You just put the Greek letters corresponding with the angular things. Okay, it's not a new formula. The v becomes omega, the r becomes theta, a becomes alpha. And I said the v becomes omega. And then you go to these kinematic equations, and then the v's becomes omegas, a becomes alphas, t remains the same, v becomes omegas. And then you just have all these formulas that are also missing. Is everybody clear on that? Okay. So if you have problems about angular kinematics, you have angular acceleration, you have angular velocity, initial velocity, it's all the same as you did for straight line motion. It's nothing new. It's just the units will be radians per second squared, things like that. Okay. Any questions? Pretty good. Okay, then let's go on. Let's see, this is probably too much zoom, but I'm going to try to magnify a little bit more than I have been doing. Just to make it a little more, a little easier to see in the back. Okay. All right, I'm gonna go in a slightly different order than in the textbook, but it's all, to me, it makes more sense to put the Newton's laws together rather than splitting one apart. In your textbook, it talks about Newton's third law in sort of in a few sentences, and then it introduces it fully later. I've always found it easier just to do it once and do it well, and then you don't have to do it twice. So let's talk about Newton's third law. Okay, so we're doing it a bit early in the book, but it's good to put them together. Okay, so Newton's third law is I am okay, so I'm going to push against this bench. I'm really pushing. Okay, so I'm exerting maybe about maybe about 200 newtons or so of force this direction on this bench. It's not moving because it's stuck to the force, okay? But I'm still exerting this force. So I'm feeling a force from the bench to me, and it's going in the opposite direction with the same 200 newtons. That's the essence of Newton's third law. That's all there is to it. So let me say very clearly, okay, let F of 1 due to 2. So there's object 1, it feels a force that's due to 2. Okay? So that will be the force on 1, object 1, due to 2. Okay, I can write the word object here, but I think it's clear. And then let F2 due to 1. So that will be the force on 2. So it's acting on the first guy due to the other one. Okay? Due to 1. Is everybody clear on the notation? Okay. Then Newton's third law is just simply the statement that F1 due to 2 is equal to F2 due to 1 with a big fat minus sign in front. Okay? So if here, let's say there's a wall, and let's say I'm pushing on this wall with some force, okay? And I'm pushing on the wall with, I said 200 newtons, and then the wall is pushing 200 newtons in the opposite direction onto me. Okay? Questions about that? That's, yeah. Yeah, that's exactly what we're going to get to in just a second. Yeah. That's actually why I want to do Newton's third law, so we can put these together. Okay, so that's pretty straightforward. Now we're going to consider an object sitting on a table. Okay? You want to visualize it, there's this box of erasers sitting on this table here. Okay, so we have some objects. There's some blocks, something, I don't know, it doesn't matter what it is. Okay, you have your table. And we're going to consider the forces on this object. So we're going to do a free body diagram. So let's say the forces on the object. Call this free body diagram. And we have the object, let's just make it a square so it's easy to draw. And we will have the force of, well, we learned last time, there's a force of gravity. Force of gravity, Fg, okay? And remember the formula for force of gravity is m times what? G, right? For force of gravity is m times g. And it goes straight down. Okay, so the way I'm drawing is the way it's supposed to be. Up is positive y. Now, there's a force that the table is exerting on the object, and this is what's called a normal force. and I'll write it as Fn. Okay, so just to label these things carefully, so Fg is the force of gravity, and Fn is the normal force of the table. And we are using the word normal in the less popular sense. Normal means perpendicular to surface. So I will often use terms. There's a surface between the object and the table. And you can be parallel to that surface, some vector parallel to the surface, or you can be a vector perpendicular to the surface. So notice it's you can't see that. It's perpendicular to the surface. It's pointing straight up. Okay? Everybody clear on that? Normal force. Okay. If you want to say it in words, normal force, let's just write it out. Normal force is the force on a body from a surface against that presses against it. That presses against the body. All right. Now, because our object is just sitting on the table, it's not doing anything. It's just sitting there. So in particular, the acceleration is 0. The velocity is also 0, but the main thing I want to get to is that the acceleration is 0. Because the acceleration of this object just sitting on the table, just sitting on this table, is 0, okay, acceleration is equal to 0, and that means from Newton's second law that F net, which is equal to m times a, must be equal to 0. Okay. Everybody's clear on that? So the net force is 0, but the net force is just the sum of the forces on it. Okay. So if I say the net force is 0, then going back to what are the forces acting on this, we have Fn going up, we have Fg going down. This is my positive y direction. And so I can say, okay, let's get the net force y component. That will be Fn goes up, so I have positive Fn. Fg points down, and that's negative, sorry, minus Fg. It's just pointing down. Okay, and we say that the net force is equal to 0, so the y component of the net force will be equal to 0. Everybody's good on that? So now the net force then, the normal force is going to be putting this to the other side. The normal force will just be equal to Fg in this particular case, which will be equal to m times g for this case. Don't learn that the normal force is always m times g, because it very well may not be. For example, if I make the table at a slant, the normal force will not be the weight of the object. It will be less than the weight of the object. Okay? Any questions about this? All right, good. So that is more or less the extent of the quiz 2 material. Now we're going to start focusing more on reviewing things that, since we covered a lot of topics really quickly, so I want to come back to something that we covered last week that I believe it would be good to do in more detail. Okay? And the demo had something to do with it as well, so it goes together. So let's say a particle is moving around a circle with radius 12 meters and speed, and I'll give you a function later, v of t. Okay, that's the speed function. And I'm going to ask some questions, but then there'll be several cases. I'll do v of t functions. Okay? So the questions are, what are the radial and tangential components of acceleration at time t equals to 0, and then also draw the acceleration, the direction of acceleration as a vector. Okay, so it's kind of hard to probe you on this with clicker questions because it's just a bunch of little questions I'll ask. So we'll just do it together. First of all, I want to make sure everybody understands the word tangential and radial. I know we did this last week, but I wasn't here last week, so I don't really know how confused people are. But you have a circle, you have some surface, some curve, okay? And here's the center of the circle. Let's say we're right here. Then let's say this is the particle. It's going around the circle, v. So this is a direction that's tangent to the circle. Everybody clear on the word tangent? Okay. So the tangential component means something in the direction of the speed. So the convention will be that if it's in the direction of the motion, it will be positive. Everybody's good on that? Okay. Now, the radial component will be pointing towards the center of the circle. You could say it's actually pointing away from the center of the circle, but let's not make it like complicated, okay? Because the centripetal acceleration will be pointing inwards towards the center of the circle. All right, so let's consider various cases. So let's do case number 1. Suppose that v of t was just constant. It was 5 meters per second. And now we're going to answer these questions. What are the radial and tangential components for the circle radius? We say the circle has a radius of 12 meters. Okay. All right, let's do this. So first of all, we'll do tangential. Tangential, and this is the formula that I just told you at the beginning of the class, is not on your formula sheet, but it's the derivative of the speed with respect to time. Okay? So if you think about it carefully, the tangential acceleration is basically like the straight line acceleration we were talking about before we did the circular stuff. Okay? It's just the derivative. You would say, but because it's going in a curve here, it's the derivative of the speed rather than the derivative of the velocity. This is dv by dt. All right, what is dv by dt for this case? 0. Okay, so there's no tangential acceleration. Now let's do the radial, or centripetal. Oh, I'm spelling it wrong. It's I then E. Centripetal acceleration. Okay, so AR, or if you want, you can write it as AC. Doesn't matter what subscript you use here. It's going to be v squared over r. And so, right, everybody remembers this, v squared over r, that's on your equation sheet. And so we have 5.0 meters per second for the speed at t equals to 0. It's actually that for every value of time. Square that, divide by the radius, which is 12 meters, and we get 2.1 meters per second squared. Okay, everybody's good on that? That's pretty quick. So this is uniform circular motion. Because it's constant speed, uniform circular motion. Okay, and so if I'm here, and my speed is, my motion is going like this, that's my velocity there, then we have this component of the acceleration, AR or AC, it's pointing towards the center of the circle, and if we want to be very clear about it, the acceleration vector is pointing, the total acceleration is pointing in that direction, because there's no tangential component. Okay. you might be asking, why did I draw this stupid thing twice? It's because I'm just saying there's no tangential component. This radial component of acceleration is all there is to the whole vector. Right. Any questions about this? Everybody good? Okay, now let's make it a little bit more complicated. Let's consider case number 2. And case number 2 is that we have v of t is equal to 5 meters per second plus 1.0 meters per second squared times t. And we want to know what are the tangential and radial components. So let's do tangential. Okay, the tangential, I said, is the derivative with respect to time, dv by dt. Okay, so we know how to take the derivative of this thing. This will give me 0. Derivative of this thing will give me 1 meter per second squared. Okay, I should have written at is equal to that. And then we have the radial or the centripetal acceleration. It's the radial direction, AR, and that's going to be v squared divided by r. And now what we need to do is just evaluate the velocity, the speed squared at time t equals to 0. Remember I said, what is it at time t equals to 0? So it'll be 5 meters per second again, divided by, and then the radius was 12 meters, so I'll get 2.1 meters per second squared. Okay. Is everybody with me so far? So at t equals to 0, that was what we're being asked. Yeah, good point. If it was a different value, we'd have to consider that. Okay, now if we're going to put it together, so let's say this is our circle. So notice this speed is getting faster. So this is the case where it's speeding up. And so here's my speed, my velocity vector. So I'll have my radial component, VR, okay? It's 2.1 pointing towards the center of the circle. But then there's also going to be, I'll just shift it away a little bit from the point so you can actually see the other line. And then there's going to be tangential acceleration like that. Everybody's okay with this? So if I'm going to draw the sum of these two vectors, this vector plus this vector, then I'll have something kind of like, that's the direction of the acceleration. Everybody clear on that? If you're wondering where I got that, so I have a piece here, I have this piece from the AR, and I have this piece here from the AT. Questions? So rather than pointing straightly towards the center, it's a little bit forward of center. Now let's consider case number 3, which I'm sure you can probably guess. Suppose v of t was something that's decreasing with time, 5 meters per second. Let's say minus 1.0 meters per second squared times t. Oops. Okay, in this case, we have tangential. At is the derivative of with respect to t. So take the derivative of this. This will be 0, but then this will give me a minus 1.0 meters per second squared. And then we have the centripetal. And this will be a r or a c, whatever you want to call it. And then it will be v squared over r. And this is at time t equals to 0. That's what the problem asked. And so at t equals to 0, we just drop this, and we get the same answer, 5.0 meters per second squared, divided by 12 meters, and we get 2.1 meters per second squared. That's maybe a little too far. Any questions about that? So now let's draw this case. So we have something like this. We have the velocity in this direction. We have the radial component going like this. And then we have the tangential thing going backwards because it's slowing down. This time it's slowing down. So if I'm going to draw the total acceleration vector, it's going to look something like this because I get a component from, so that will be this guy. So I'll get a component from the AR, and I'll get a component from the AT. So it's this vector here. Okay, any questions about that? Everybody got it? So it's a little bit backwards from pointing towards the center of the circle. All right. Let's now let's do some problems. Let's start off with a quicker question. Okay. So this comes from one of the practice tests that I had before, from when I was teaching at North Carolina State University. Let us do number 11. Let's move it in. Okay, there's no choice D, so that don't choose that one. Okay. An ant runs due east at v equals to 0.2 meters per second relative to a wagon that it is on. It's on. The ant is on a wagon. Okay. If the wagon is moving due north at 1.5 meters per second relative to a person on the ground, at what speed is the ant running relative to the person on the ground? Okay. So let's open this up. Go ahead. Yes. Okay, I'll give you another 30 seconds to work on it. So while we're waiting for people to finish up, there's a lot of resources on your Geek Flow webpage. You may may not be aware of. As I said, there's now practice quiz number 2 up there. There will be solutions posted after Thursday's session for that. Then there's the formula sheet that I was telling you for quiz 2. There's also all your quiz 1 stuff. So there's your quiz 1, the actual quiz and the quiz solutions, some detailed solutions that you will not be typed up. All your scores, homework scores and stuff is on the Google webpage. As well as your quiz answers when you for your finding whether you got a given problem right or not. So 1 or 0. What else? I've also posted, aside from all the lecture notes and videos and stuff, I posted a folder of all of these practice problems, a lot of stuff relevant for quiz number 2 there that you can work on if you're looking for extra problems. Okay, well, let's take a look at what people said. All right. Looks like C is a little bit more popular than all the others. So let's take a look. All right. What do we know? So let's write it this way. We have V ant relative to wagon. Let's use unit vectors. So this is due east, they say. Okay, 0.2 meters per second, and that's relative to the wagon. So I will, because I'll call this the plus axis, x-axis, and this is the plus y-axis. It will be I hat. Everybody's good on that? Okay. Now we know. Okay, so I'm going to take the person on the ground as being sort of the absolute non-moving person. And my experience when I'm teaching this topic of relative velocity is to not say person on the ground, because that makes everything look equivalent. So I'll just make person on the ground, and I'll skip saying that because that's sort of like the absolute stationary person. So I'll just say the velocity of the wagon. And the velocity of the wagon, they say the velocity of the wagon is going north by 1.5 meters per second, and it's in the I hat direction. Okay, everybody's good on that? J hat. Should be J hat. Right? Did I say I? No. Okay, sorry. Sometimes my mouth says the wrong thing, and I don't even know. A J hat. Okay. Now, what we want is the velocity of the ant. Okay, relative to the person, but on the ground. But remember, the person on the ground is the non-moving person. So just the velocity of the ant. So I can say that the velocity of the ant is equal to, there's many ways to do it. I can say it's the velocity of the wagon, so that's supposed to say velocity of the wagon, plus the velocity of the ant relative to the wagon. Everybody's good on that? Okay. The velocity of the wagon plus the extra amount the ant is moving relative to the wagon. And so I can put that together. And so I have 0.2 meters per second I hat plus 1.5 meters per second J hat. So these are my components. So if I want to get the magnitude of the velocity or the speed of the ant, it's the square root of the sum of the squares, 0.2 squared and 1.5 squared. Okay. And that comes out to, okay, because 0.2 is kind of small, it turns out when you round it's 1.5. So it's kind of simple. All right, any questions? All right. I mentioned that there were some practice problems on various topics. Here's one little worksheet. There's some relative velocity problems that I put up. These problems are a bit like the one we just did, these first two. The reason I did this was was for a homework assignment back, when the heck was this? This was in spring 2016, okay? You see, this is proof I've taught courses on this before, okay? And and this was a homework assignment that the students hated because the problems were really tough. And so we went over some of these solutions for these problems. So take a look at these two. I'm not going to do these two because they're kind of similar to each other, and they're kind of similar to the one we just did. Okay? But I'm going to take a look at the one on the back, which is different. It's a little, and this is the one that tripped people up. And let's see, maybe I need to zoom out a little so you can actually see it completely. I can zoom back a little bit. Yeah, that just about fits now. Okay. All right, I'll read. I know the resolution is not so good, so I'll read it out now. A woman starts to swim directly across a 4.8 kilometer wide river. Her speed with respect to the water is 2.3 meters per second. The river current carries the woman downstream at a speed of 0.91 meters per second. Okay, so the width of the river is 4.8 kilometers. Her speed is 2.3 meters per second with respect to the water. All right, the question is, now you see the solution here, but why don't you, this is not a clicker question, but why don't you try to see if you can get this answer. Okay, this is the thing that the students in this class from 2016, I taught, had trouble with. All right, see if we can get to 2,087 seconds. It's not a clicker question, but go ahead and see if you can get that. So if the number is a little small, the river is 4.8 kilometers wide. Her speed with respect to the water is 2.3 meters per second, and the river current carries the woman downstream at a speed of 0.91 meters per second. And so there's a little thing to think about is you can think about the woman's trying to go across the river here. Okay. Just give that a shot, and then we'll go over the solution. I don't want to just go over the solution before you give it a try. I'll wait a couple minutes. So the water is moving, but you're floating with the water. You see her move with that. In other words, that's how fast she swims if the water wasn't moving. The thing is, it's actually a really simple problem, although it looks like it's a really complicated problem. It's how fast the river is flowing. Yeah. That's right. Yeah, that's right. Yeah, so the river is flowing 0.91 like this. She will move 2.3 meters per second. Okay? She's going to move, She's going to go directly across, and the question is how long does it take? Okay, since it's not a clear question, I'm going to start telling you the solution maybe it's away. Now, the thing you're supposed to notice here is that this woman just wants to get across the river. Right? She doesn't really care where she ends up on the other side. She just wants to get across the river. And so the way I've drawn it here, the crossing the river is in the x direction. Okay? The flow of the river is in the y direction. So from the point of view of how long it takes us to cross the river, the fact that the river is flowing has nothing to do with how long it will take her to cross the river. Do you see that? It'll just carry her down the river as she crosses it. If the river was not moving, she'd just cross at the same time. So that's the beauty of this problem. She's moving 2.3 meters per second directly in the x direction. So we have a distance of 4.8 kilometers is 4,800 meters. We just divide by her speed, and then that comes out to 2,087 seconds. Okay? That's all there is to this problem. You got that? Okay. Now, for those of you who are thinking, oh, that's too slick, I could never figure that out. Let's just do it step by step and just work it through. Okay? So if I'm saying, all right, so what we're told, the velocity of the woman relative to the water, that's what it says, woman relative to water, that's going to be 2.3 in the x direction, so 2.3 comma 0. Okay? Everybody's with me on that? Woman relative to water. The velocity of the water, okay, so the velocity of the water is 0.91 in the plus y direction, so 0 comma 0.91. So if I want the velocity of the woman, it will be the velocity of the water, which I have here, plus the velocity of the woman relative to the water. So then I add these two together and get 2.3 comma 0.91. But now what we say is how long does it take to go across in the x direction? And all this stuff we bothered to calculate doesn't matter. Okay? And so we just simply say the time is delta x over the x component of the woman. And so we get 2,087. Now, the river does make an appearance in the second part of the problem. How far downstream will the river carry her? Now that you know how much time, then you can calculate how far the woman drifts down. It will just be the 0.91 times the time, 2,087. Okay, and that comes out to 1,899 meters. Any questions about that? Okay, I'll see you guys tomorrow.